let me go over question 13 and quiz 2. Dr. Marco asked me to go over it, so if anyone has any questions, go ahead and ask them. So in question 13 and quiz 2, you are given a transfer function given by this expression here, where a is a parameter that is equal to 9. And we would like to compute the steady state error for this transfer function when we close the loop using a unity feedback. So the steady state error is basically equal to 1 minus t of s times r of s. Okay, and we get that expression because the steady state error is just going to be equal to r of s minus y of s. R of s is the is the input to the system. Y of s is the output. So the output is just going to be equal to t of s, which is the closed loop transfer function, minus r of s, which is the input. So you take r of s as a common factor, you get the formula above. Now you compute 1 minus t of s. 1 minus t of s is just going to be 1. So 1 minus t of s is just going to be 1 minus g divided by 1 plus g, right? So you can just do this some algebra and you get that 1 plus over 1 plus g is going to be equal to 1 minus t of s. So this is the expression here. When you substitute with g of s equal to the expression you're given in the problem, you'll get that 1 minus t of s is going to be s plus a divided by s squared plus s plus a plus 4. And we have that the input is going to be 1 over s. So now we want to compute the steady state. So, and to do that, we use the final value theorem, which says that the steady state error is going to be the limit of s times e of s. Now we see that s times e of s is going to be equal to, so it's going to be equal to s times 1 minus t of s times 1 over s. So the s cancels with the s and you get this expression only. So the limit of that is just going to be equal to a divided by a plus 4, which gives 9 over 13. So that's the steady state error for this problem, which is going to be equal to 9 over 13. Okay. Any questions? Hopefully not. Let me just erase these quickly. All right, so the first problem we have for today is we are given a feedback system that has this closed loop transfer function. And let me just emphasize the fact that this is the closed loop transfer function, not the open loop. So we'd like to determine the poles of the system, the zeros, the system type, and the steady state error due to step input and a ramp input. Okay. Erase them as we go. First, we want to emphasize that if we have a transfer function, if you have any transfer function, let me write that this is t. Okay. If you have a transfer function t of s that is equal, it's going to be equal to n of s. This is the closed loop transfer function. We can write it as the ratio between two polynomials, the numerator polynomial n of s and the denominator polynomial d of s. Then the poles of the system are basically the roots of the equation d of s equal to 0. Okay, these are the loops, the closed loop poles of the system. So in this case, in our system, we just basically the poles are basically the solution to this equation, and the zeros are basically the roots of the numerator polynomial equal to 0. This gives us an equation. We solve, we get the zeros of the system. And remember that the zeros of the system are basically, from our previous discussion, we can understand them as that they are, or whenever you give an input into the system at the same frequency as the zeros of the system, that input is not going to appear in the output at all. Like you will not see it in the output at all. Okay. So going back to solving the problem, right? We have s squared plus 3 plus 3s s cubed plus 3s squared plus 3s plus 1. This is just s plus 1 cubed, right? So we equate that equal to 0. We get that the poles of the system, or the closed loop system, has 3 poles at -1. So it has a repeated pole, right, at -1. And the zeros of the system, which are the zeros of the numerator polynomial equation, right? It's just going to be, so I just used lambda here for let me just put it back here. This is s squared and this is 2s. And so this is just the roots of the equation are going to be given by the quadratic formula. And they will be given by, yeah, so this is a plus -1 plus or minus this. Okay, so far so good, nothing fancy. So the roots of the equation, basically the zeros are given by these two complex numbers. So let me also erase this. So these are the poles. So now we have found the poles and the zeros of the system, right? Next, in the question, we want to find the system type. Okay, so the system type is basically the, we can recall that it's basically the number of poles of the system at the origin, and it's important to emphasize this here for the open loop transfer function, right? Here we are given the closed loop transfer function. So to obtain the system type, we need to obtain the open loop transfer function, right? And so the open loop transfer function is, we know that the closed loop transfer function is just going to be equal to t, which equal to g divided by 1 plus g, right? So we can solve this equation for g. If we just do some manipulations, you will end up that g is going to be equal to t divided by 1 minus t. So when you substitute with the expression for t that we have, we get that g of s will be given by this expression here. And we see that this expression does not have any poles at the origin, right? It does not have any poles at the origin, which means the number of poles is 0, which means that the system is a type 0 system. If we had one pole here, for instance, at the for the open loop transfer function, one pole at the origin, then we say that this is a type 1 system. If 2, it's a type 2 system, and so on. Any questions? Okay. Moving on. If you have any question at any point, just stop me and I'll be glad to answer. Okay, just make sure that everything is clear. Okay, so then now that we've calculated the system type, we would like to we look at the steady state error. Okay, so again, the steady state error is E of s is going to be equal to R of s minus Y of s. Y of s is the closed loop transfer function times R of s. So this is R of s minus D of s times R of s. Then this means that E of s is just going to be equal to R of s times 1 minus D of s. 1 minus D of s we calculated to be equal to 1 over 1 G of s times R of s, right? So this is the final expression for E of s. Now, before we apply the final value theorem, we need to ask ourselves whether or not the final value theorem is actually applicable, right? Because what we do to calculate the steady state error is that we apply the final value theorem. And to apply the final value theorem, we need to make sure that its assumptions apply. And one on the main assumption is that T must not have any right half plane poles, right? Luckily for this system, we see that t, which is the closed loop transfer function, does not have any right half plane poles. In this case, we know that final value theorem is applicable, and we can continue to calculate the steady state error. So, so the steady state error is defined as the absolute value of the limit as s goes to 0 of s times e of s. Okay. So for a unit step input, we know that r of s is equal to 1 over s, right? So 1 over s, if we calculate s times e of s, it's just going to be equal to 1 over g of s, right? Times s times 1 over s. So the s cancels with the s, and we get that. So s times e of s is just going to be equal to 1 over g of s, right? So the limit of that as s goes to 0 is just going to be equal to 1 over 1 plus g of 0, right? So the absolute value of that. So at s equal to 0, g, if you go back here and put s equal to 0, we get that g of 0 is going to be equal to 3 divided by -2, which is negative 1.5. We substitute with that in here, so we get that that ESS is going to be equal to 2, right? So the steady state error for this transfer function due to a step input is 2, right? Now we move on to look at the steady state error due to a ramp input. Okay, a ramp input is given by 1 over s square, right? So now we do the same calculation again. It's 1 over g of s times 1 over s square in this case, right? So the 2 or the s does not cancel completely with the s because we get an s, right? There's an s that remains in the denominator. So when we try to take the limit as s goes to 0, it turns out that this limit will be plus infinity, right? So the steady state error for this system is actually infinity. And we expected that because this is a type 0 system, right? And so for a type 0 system, when you try to give it a ramp input, you will get that the steady state error will actually grow to infinity. Okay, any questions? Okay, moving on. The second problem we have today is that we are given an open loop transfer function, and we would like to compute for this open loop transfer function, k divided by s squared plus s plus 3, we want to find the range of values for k, right, such that the steady state error due to a step input is less than 10%, right? And then next, we want to modify this transfer function, right, either by adding poles or zeros, such that we find a range of values for k, again, a range of values for k, such that the steady state error due to a ramp input is less than 5%, okay? Again, T of S is just G of S divided by 1 plus G of S, which after you substitute with the expression here, you get that it's going to be K divided by S squared plus S plus 3, right? And there's an easy way to do this. Now, if you have that G of S, the open loop transfer function, again, can be written as N of S divided by D of S, right? So now we have the G of S divided by 1 plus G of S is just going to be equal to N of S divided by D of S. Everything divided by 1 plus n of s over d of s. So you multiply the numerator and the denominator by d of s. You get that, that the t, or the closed loop transfer function, will be n of s divided by d of s times plus n of s, right? And n of s in our case was k, this was k, and d of s was just s3 plus what was it actually? Yeah, s squared plus s plus 3, right? So this is what we got here in this expression here. So because we have the open loop transfer function g, right, we see that it does not have any poles at the origin, which means that which basically means that this system is a type 0 system, right? And for a step input, again, we have s times e of s will be equal to 1 divided by 1 plus g of s, which means that the steady state error is just going to be equal to 1 divided by 1 plus g at 0, absolute value, which is just going to be the absolute value of 1 over 1 plus k over 3. Now, to have a steady state error of less than 10%, this implies that we want the absolute value of 1 plus k over 3 has to be bigger than 1 over 0.1, which means that it has to be bigger than 10. So when you try to solve this inequality, you get two ranges, right? Either that you get either that k is bigger than 27 or that k is less than 33, right? So for instance, let's try 27. 27 divided by 3 is going to be equal to 9. 9 plus 1 is going to be 10, right? So the absolute value of 10 is equal to 10, so it satisfies the inequality. In the other case, if k is less than 33, this means that k divided by 3 is negative 11, plus 1 is negative 10. The absolute value of that is going to be 10, right? So both of these ranges satisfy the inequality. However, one of them has to be rejected. Any ideas why do we reject the range k less than 33?
Because you can't have a gain that's less than 0.
Well, you can, but in that case, the gain just points in the opposite direction. But what happens when k is negative? There's something particular happens when you take k negative in this transfer function, for instance, in T of s. Like, let's say we take k to be equal to negative 1, right? You still get a plausible transfer function, right?
Wait, is it going to cause the output to explode? Because is it going to turn one of the poles positive?
Exactly, right. So if, for instance, if we try to put k here in this denominator, if you put k with negative 4, what happens? You get a negative 4 in the numerator, right? But you also get s squared plus s minus 1, right? So that's the roots of that are going to be equal to like you will have one of them is going to be positive and the other will be negative, right? Which means that you will have a pole in the right half plane, which means that the final value theorem is no longer applicable, correct? So so we have to be careful that whatever range of values k here, it must be consistent with the assumption that we made in order to use the final value theorem, which is that the closed loop transfer function must not have any right half plane poles. So we see that if k is bigger than 27, this is consistent with the assumption that the final value theorem applies, which means that we can actually easily, we can, or like if you substitute with 27 here or any larger value, you will get a transfer function that is perfectly stable. So you're good. You can go on, and this range is actually an acceptable range for k, right? So if you have k is bigger than this value, you will satisfy the steady state error requirements to do a step input, and also your system will be stable. And we'll see later on what do we mean by stable. So this is a type 0 system, right? So as we calculated in the previous problem, we already know that if you try to apply a ramp input to this system, the steady state error is going to grow to infinity, right? That's what we calculated in the previous problem. And so in order to make the system stable, or to make the ramp input, or make the steady state error due to a ramp input finite, you need to change the type of the system, right? In this case, you want to change the type of system from type 0, you want to make it a type 1 system, right? Because the type 1 system is the type of system that will have a finite steady state error due to a ramp input. Okay, so basically that's what we do here. We add the pole at the origin for the open loop transfer function without closing the loop. So we get k divided by s, right? Multiplying the denominator that was already there, s squared plus s plus 3. Now this is a type 1 system, right? So we calculate the closed loop for that. Again, it's going to be k divided by s cubed plus s squared plus 3s plus k. So after you do the manipulation as before, you get that E of s is going to be equal to s cubed plus s squared plus 3s divided by s cubed divided by s squared plus 3s plus k times r of s. So, okay. Moving on. So E of s, E sub ss is going to be, again, this is the steady state due to a ramp input, right? It's the same for all of them. The limit as s goes to 0 of s times E of s. Now the expression for E of s will be this expression that we used. This expression that we used here, right? After you do some manipulations, it turns out that, so we know that the s, this s cancels with one of the s's in the ramp input, right? So you get a, you get 1 over s that still remains. However, when you calculate the E of s, it turns out that you will have an extra 0 here, right? So you can factor s out of this polynomial. It's a third order polynomial, so you can factor s out of it. And that s cancels with the other s. So you end up with, so let me do this. So this cancels out. And you end up with a finite finite value for k, right? In this case, or finite value for the error, which is just going to be equal to, when you put 0, it's going to be equal to, so this is actually 3, right? Yeah, this is 3. I need to correct these notes. All right, so yeah, there we are. So this is 3, right? Because we will have here s squared plus s plus 3. So this is 3 divided by the absolute value of k. So to get a steady state input less than 5%, we need that k has to be equal to 20 over 3, right? The absolute value of k has to be bigger than 3 over 20. No, 20 over 3. Yeah, right. No, wait a second. Yeah, we want this to be less than or equal to 1 over, or 5 over 100. Right, yeah. No, actually. Yeah, that's actually, yeah, you actually want that k has to be bigger than 3 times 20, which is 60. Oh, wow. Yeah, that makes sense. Yeah, so you have that k has to be bigger than 60, right? Okay, so this is 60, and this, or that k has to be less than 60. Now, again, we know that the negative values are going to be rejected for obviously, because if you put negative 60 here, you will definitely get a pole in the right half plane, right? Now, but is actually the range of k bigger than 60, is this range acceptable, right? Again, in order for it to be acceptable, we must have the final value theorem be applicable, right? Otherwise, if it's not applicable, then we cannot have this, we cannot apply it, and so the analysis is not correct. So suppose that k is equal to 60. Okay, we get 60 here and 60 there. So we want to find the poles, right? We want to find the poles of this, the closed loop transfer function, which are the roots of this polynomial equation, right? Now, now to do that, we can, of course, you can use MATLAB or you can use a calculator, or, but I'm just going to teach you a way that Dr. Marco is going to probably use this later on, because so basically, when you have an equation that you would like to determine its roots, in this case, it's 60 here, right? So this is the equation. You want to find its roots, right? And you take the derivative of it. It's going to be 3s squared plus s plus 3. And you use Newton iterations, which basically means that the next value in the iteration is just going to be equal to the previous value minus d evaluated at the previous value divided by the derivative evaluated at the previous value again. And you start from some value, say is x0 equal to 1. In this case, actually, I need to do the calculations again. Come on. Okay, x minus x cubed plus x squared plus 3x plus 60 divided by 3x squared plus 2x plus 3. Okay, so 1 store x. All right. So the first iteration will give that x is going to be equal to negative 7.125. The second iteration will give negative 5, approximately negative 5.94. The third iteration will give negative 4.26. The third iteration will give negative 4.01. The next iteration will give negative 4.00. And so on. So you see that it's actually going to converge to negative 4, right? That actually makes things easier. So we see that we will have a pole at negative 4, right? So this is one root, right? So which means that one of the factors of the third order polynomial is going to be equal to s plus 4. So what about the other two factors, right? Because this is a third order polynomial, so we have 3 factors. This we basically gonna have to do long division. So that's what we do here. This is 4. Yikes. So this is 4s squared So the s cubed cancels, you get negative 3s squared, negative 3s plus 20. This is actually a plus. All right, so negative 3s divided by that, you get negative 3s. So negative 3s plus, or sorry, negative 12 s. So you subtract that, you get, well, these cancel. Use red to be consistent. These cancel. So you get 15s plus 20. Wait a second. S cubed plus 4s. Oh, yeah. Oh, God. So s cubed plus s squared plus 3s plus 60. Yeah, that's the problem. Okay. Yeah, so this is, again, this is negative 3s squared plus 3s plus 60. Negative 3s minus, so you get negative 3s, right? So this is again negative 3s squared, negative 12s. So this cancels, and you get 15s plus 60. Again, this that you divide by that, you get a 3 here, and then sorry, you get 15. So you get 15s plus 60. So this is 0, and so this is the factor that remains, s squared plus 15, minus 3 plus 15, right? So we can actually, so let me remove that and write, this is going to be exactly factored as s plus 4 multiplying s squared minus 3s plus 15. So the two other poles can be given by the quadratic formula, right? Which are basically the roots of this factor here. So you have negative 3 plus or minus square root of 4. So basically this is 9 minus 60 divided by 2. Which is just going to be equal to negative 3 over 2 plus or minus square roots of, so this is I, and then you have square root of 54 divided by 2. This is actually a plus, and this is a plus. Yeah. So the important thing here is that we will have a right half plane poles, right? So this means that that the P2 and P3 are actually in the right half plane, which implies that the final value theorem is not applicable. Okay, so even K, when K is equal to again 60, this we cannot actually achieve that, right? So so the final value theorem will not applicable, and so this steady state error cannot be calculated this way. In fact, if you try to calculate or do this calculation for any higher value, like if you do for k bigger than equal to 61 or any bigger value, you will actually arrive at the same conclusion in the sense that the poles of the transfer function, of the closed loop transfer function, will lie in the right half plane. So in particular, it turns out that actually we cannot achieve ESS less than 5%, right? So even this range is not applicable. Yeah. So this range is actually not applicable because of the final value theorem. And we will see that more on this. We will cover this when we go to cover stability. Finally, the third problem I have for you is basically we want to find we want to use MATLAB to find the range of values k that achieves the minimum ESS due to a ramp input for this problem. So I wrote the script and I attached it here for your reference. But let's just go and explain over MATLAB. It's easier that way. Okay, so want to share screen? Yes, screen one. Okay, so so this is the code, right? This is the function. We want to find the minimum value k. It takes as input an array of k's. Okay, this is an array of values and values of k, and then it computes the one that achieves the minimum steady state error among all the values inside the range k. So let me explain the code line by line. S equal to T of S. This is just to simplify when we try to write any transfer function later on. So now if you want to write a transfer function, you can just use S as the frequency parameter instead of using the transfer function TF each time. So G equal to 1 divided by S divided by S squared plus S plus 3. And you see that we're missing K here, which represents the our parameter, because I'm gonna do a loop over all the values in K, so I just don't write it in the expression here. Now, and then just basically, this is an initial array that we will add to it as we go on. We will add to it the valid case. By valid, I mean those for which the final value theorem is applicable. Okay? So we do a for loop. It goes over the array k range. Okay, and then at each entry, we just basically pull out the value for k, and then we compute the closed loop transfer function using the function feedback, which takes in two factors. This particular syntax in the first factor, you get you will put g, and then in the second one you put 1. So this is equivalent to k times g divided by 1 plus k times g. This particular syntax is equivalent to that. And then we have a function that checks whether or not t has right half plane poles. If it has right half plane poles, then we skip the remainder of this loop and move on to the next value in the array k range, right? If it does not have any right half plane poles, this means that this is a valid value for k, so we can add it to our array valid k, okay, using this simple syntax here, which basically says that valid k is equal to whatever was in valid k before, and then we just add the new value k range at this particular index that for which so we can actually put here k at this particular index for which t has no poles, right half plane poles. And then we compute ESS. Okay, it's just going to be equal to 1 over k, the absolute value of that. And you notice the element-wise division here. So I'm dividing by, like this is an array, so I'm flipping every element in it. And then finally, we use the function minimum. This is a built-in function in MATLAB. It takes in an array and finds the minimum state and the minimum value in this array and the index of that minimum value. So we use that syntax here. This is e minimum, and this is the index of the minimum. value, and then we extract the minimum value from the valid case by basically using the minimum index. Then we just display that in just for convenience. Now the function right half plane polls takes in a transfer function t and returns a flag that is either true or false. The poles, first we compute the poles of the transfer function. You can do that using pole of t. Okay, pole of t. This is a function in MATLAB that basically computes the poles of a transfer function. You give it a transfer function, it returns an array containing all the poles. And now, because some of the poles will be complex, we just basically extract the real part of them, right? So we use the function real. Real will give us the real part of the poles in this poles list array. We put that in the real part, and then we basically say if any of these roots has or if any of these poles has a real part that is bigger than 0, this means that we have right half plane poles, right? So in this case, we want that the output flag to be true, which means that okay, my transfer function has a right half plane pole. If not, right, none of the values in this array has a right half plane pole. This means that we put the output flag false, in which case we go to this part of the loop. Okay, very well. So let's try to give this a run. Now, suppose that we have the range of k is going to be equal to from 0.1. We can actually put something here like from that's -1, let's say, up to so 60 is actually problematic. So let's do instead from 50 up to 60. Okay, with a step of or we want a total number of 100 elements in this range. So okay, so this lint space takes in 2 numbers and returns a vector that is equally spaced, starting 50 and ending at 60, and has this many like this many elements. Okay, so if you look at k range here, we see that k range is 1 times 100. So k range of 1, this is just 50, and k range of n, this is just 60. So now we look at our function and we try to compute this, right? So it turns out that the values from 50 to 60, none of the values is actually a valid value for k, right? We can see that k minimum returned an empty array here, and e minimum is also empty, which means that none of the values in the range k actually contains a valid k value. So let's try something else. Let's try that k ranges instead goes from 0 up to 5 with a step of, let's say, with 20 elements in this range, for instance. Okay. Now let's run this again. We see that the minimum steady state error we got for these values of k is 34.5%. And the corresponding k is approximately 2.9, right? Now, if we try to increase this range a little bit, or increase the number of elements in this array, let's say 100, and run this simulation again, or run this loop again, we see that the minimum steady state error is now, or that can be achieved, is 33.5%, and k is 2.98, right? If we try to increase the range further, let's say take 500 elements instead, and do this process again after longer computation, we see again that k is so it displays here that k is approximately equal to 0, but it's not actually equal to 0. Like if you look at k min, it's going to be equal to 2.9960, whatever, right? So can someone tell me what happens at k equal to 3? Our range includes values from 0 to 5, right? So, however, no matter how small we make our step size, we cannot, or it seems that we do not cross k equal to 3. So something happens at k equal to 3. Can someone tell me what? Any ideas? Okay, so it turns out that if you put k equal to 3, like let's try to compute k equal to 3. Okay, now we have, this is g, right? We want to do a feedback of 3 times g and 1. So it turns out that, wait a second. Yeah, right. So you get this transfer, function, right? So if you look at the poles of this transfer function, let's look at the pole. You see that you will have a root or a pole at -1, right? And 2 imaginary poles at 1.73 and -1.73i, right? These 2 poles, if you try to increase k any further, they will actually move into the right half plane, which will make the system unstable, which means that the system actually will not, or that we will not be able to apply the final value theorem any longer, right? Because we have right half plane poles. So the message that I'm trying to emphasize here is that k has to be, or that in order to apply the final value theorem and correspondingly compute the steady state error, you must make sure that your transfer function does not have any right half plane poles. That's the first thing. The second thing is it depends the system type, or depending on the system type, you might have the steady state error. Steady state error might be finite or infinite, or might actually be 0, right? Depending on the system type and the type of input that you give to your system. So that concludes my discussion today. Thank you for your attention. Any questions before we go? All right. Thank you guys for your attention, and good luck.
Thanks, Mahmoud. It was helpful.
Thank you.